Professor Somnath Basu from IISER Kolkata. So he'll be speaking on and around loop spaces. So Somnath, it's now up to you.
Okay, thank you, Abhijit. And to reiterate what Abhijit said, I would like to thank Shomyo and the other organizers, presumably a lot of other people who were in the background while making this successful event, an event of this scale, in the context of this pandemic. So, so thank you for the opportunity. So I would like to talk about my thoughts on loop spaces. And this is going to be the title, as you can see, on and around loop spaces. And I'm going to basically go in a circle talking about a few topics which present themselves in the context of studying and understanding loop spaces. And I'm going to start with, so I mean, these are symbols as of now. Hopefully they'll make more sense as we go along, but I'm going to start with this first topic, which is this quantity, which is nabla gamma dot gamma dot. So that's our starting point. Okay, just a second. So these are called closed geodesics. If you set it equal to 0, then for those of you who have taken Riemannian geometry, a geodesic is defined by the equation nabla gamma dot is 0. But let's take let's take a step back and ask, what is a geodesic in general? Well, in the context of metric spaces or metric geometry, these are what are called locally length minimizing curves. Okay, since we are going to be interested only in the Riemannian context, what does it mean in Riemannian geometry? Well, informally, these are locally everywhere length minimizing smooth curves. So typically these are C2 curves, but we're going to assume these are smooth curves. So this is a good definition in the sense of giving you an idea of what it is, but it's not a good definition in terms of computing things. So how do we actually define a geodesic? Well, there has to be some differential equation that it satisfies. And usually the formalism that you see is that you start with what's called the energy of a path. So here we have a smooth path defined on an interval A to B. I'll call that path gamma. And the energy of the path is defined to be simply, you take the velocity gamma dot, take its absolute value or the speed, take its square. So that's what this inner product gamma dot means. It's the speed square, and you integrate it from A to B. And there's a normalizing factor of half. So this is what the energy of a path or a loop or a curve is. And one can ask, what are the critical points of this energy functional? Okay, and the answer is the critical points of this energy functional are precisely the geodesics. Okay, they actually are locally length minimizing among all curves joining gamma A to gamma B. So if you use the calculus of variations, then there's a formalism called the Euler-Lagrange equations, and the Euler-Lagrange equations will tell you what these critical points ought to satisfy, and it satisfies a system of differential equations of this form. So again, I'm writing my curve gamma t in local coordinates. In a manifold, in a local chart, you can have coordinates x1, x2, xn. So here my gamma t is of the form x1 of t, x2 of t, up to xn of t. And these coordinates in terms of t should satisfy these system of equations. So this is like the acceleration of xk. So delta d by dt2 of xk plus these products of these dxi dt, dxj dt. But there are these constants which should remind you of something that you already know. These are called the Christoffel symbols associated to the Riemannian metric. And given the Riemannian metric, one can write down these Christoffel symbols, which are in terms of derivatives of g. And then one can solve this locally using Picard-Lindelof, and you know that your geodesics exist locally, and they're unique given initial conditions. Okay, so these are what geodesics are. So this is the formal setup, but for those who have not seen Riemannian geometry, well, let's try to see what it is for simple examples. So for Euclidean spaces, the usual Euclidean space Rn with the standard metric, it turns out that metric is flat. So the geodesics, as we know from childhood, these are straight lines, right? Okay. What about spheres? Well, these are spheres, unit spheres or spheres of some radii inside Rn plus 1. Rn plus 1 has the metric as discussed above here. But when you restrict that metric to any submanifold, namely the sphere, what you get is a round metric. It's called a round metric because the curvature is everywhere the same and it's positive. It's actually 1 over r square. And the geodesics on the spheres are nothing but great circles or parts of great circles. And we already know that from our experience in traveling around the globe that the plane tends to take the arc along a great circle, typically when you try to fly from point A to point B. Okay. So what about the hyperbolic plane? Well, this is it's upper half space, but the metric is not the usual metric from R2. The metric is somewhat different. If you have seen the metric, you already know what it is. If you haven't, then you might be interested in looking up what is called the Poincare metric. And this is a metric which is special because it gives the hyperbolic plane a constant negative curvature -1. Okay, so it becomes negatively curved, and the geodesics on the hyperbolic plane are basically going to be all either straight lines perpendicular to the x-axis, so this is the x-axis which is missing, or semicircles which are perpendicular to the x-axis. So these are all the geodesics on the upper half plane. Okay. So one thing you should note is that among these three examples, the only case where we actually get closed geodesics or periodic geodesics or loops which are geodesics is the case of the sphere. In the case of the plane or the hyperbolic space, these geodesics are not closed geodesics. Okay? So one might wonder whether compactness has something to do with even obtaining a closed geodesics or a periodic geodesics. They're used interchangeably here. So that's a natural question that you have. Does compactness ensure the existence of one non-trivial periodic geodesic? And by periodic, I mean it should be a smooth curve, which is a geodesic such that gamma has a period. It's defined over the whole real line. Non-trivial means that we are not interested in the constant curves. The constant curves are obviously geodesics. They satisfy the differential equation that I set up earlier, but we're interested in non-constant geodesics. So that's what I mean by non-trivial. So, okay, so that's the question. So if I ensure compactness, does it mean that I always have a non-trivial closed geodesic? So let's see. So to talk about geodesics further, I have to introduce one of the objects already appeared in the first slide. This this object called LM. So L stands for loop. So LM, we are going to call this the free loop space. And what is this? Well, this is nothing but the space of all continuous maps from the circle to the manifold M. So for those of you who have seen a bit of topology, you know that this space has a natural topology which on it called the compact open topology. And so it is a topological space. Okay. And we are interested in this space simply because we are looking for closed geodesics. And closed geodesics are simply going to be some special curves in this space, right? So we are not interested in random geodesics which are defined over an arbitrary interval. We're interested in closed geodesics. There's a cousin, which is the smooth version of this, which is denoted by script LM, which is all piecewise smooth curves from S1 to M. Okay. So this is slightly better behaved in terms of doing some sort of infinite dimensional analysis and so on. It turns out that these two spaces, the continuous free loop space and this smooth cousin, they are homotopy equivalent. Okay. However, as I said, each one has its own advantages in terms of what you want to do at that point. If you want to do more geometry, maybe script LM is better. If you want to do more topology, algebraic topology, maybe LM is better suited. Nonetheless, the closed geodesics live inside both of them. Okay, there are special curves in here. And in fact, if you go back to the first slide, we talked about the energy functional, and the energy functional is still defined on either of these two spaces, right? The point is that the energy, I mean, it's definitely defined on the latter one because this is piecewise smooth, hence piecewise differentiable. And we want the critical points of the energy function to be the geodesics. So we are really in secret trying to study the energy function on this infinite dimensional space, which we cannot as of now. So let's see what happens when, so having said that, let's see what happens when M is compact. Well, when M is compact, it turns out that there is a chance that you can get a non-trivial closed geodesics. So there's a topological argument that if pi1 is non-zero, then there's something called curve shortening, that if you choose a non-zero element in your fundamental group, choose a curve representing that element, and try to basically represent that curve by other curves which are homotopy equivalent but having smaller and smaller length, and you shorten the length, and if you can obtain a curve which realizes the shortest possible length, then it turns out that curve is indeed actually a smooth curve and actually a geodesic. So this is Birkhoff's famous curve shortening process, and this tells you that you will always find non-trivial geodesics if you choose a non-trivial element in pi1 which relies on the fundamental group being non-zero. But this process wouldn't work if the manifold is simply connected, because you simply do not have any non-trivial loop, any non-trivial element in pi1 to begin with. The only element that you can choose is the trivial loop, and the trivial loop is represented by the constant geodesic, which we don't want. So then Morse theory comes to the picture, and Morse theory helps you prove that indeed if M is compact and pi1 is even if pi1 is 0, there is going to be a non-trivial closed geodesic in every component of Lm actually. So Lm will have lots of components. In each component, you're going to find a non-trivial closed geodesic. And this is basically a line of reasoning following Morse, where he introduced Morse theory, the theory that bears his name these days. And one of the applications of that theory was this. Okay, we'll talk about some other applications later on. Okay, however, if you think that okay, all of this is nice, just take this simple example. This is like a bumpy sphere. Okay, just imagine that you took some actual old cricket ball and then you know like dipped it inside some like warm chocolate or warm mud, and then you pulled it out and it had all these peaks and bumps and so on. And I couldn't draw as many peaks as I wished, but imagine that there are way more peaks of different heights and different sort of radii. And so now imagine yourself being a traveler on this bumpy earth, so to speak, and then you're just trying to start at a point, and then you're traveling along a geodesic and hoping to come back and close it up. And if you imagine for 1 second that you can close it up, you'll see that at every point you hit one of these peaks, you cannot really go up the peak, because that wouldn't be locally length minimizing. You have to go around the peak either right or left. But if the peaks are sufficiently, like densely placed, you have to always make a choice of right and left. And then by the time you come back to somewhere close to where you started, you might have already taken a different direction and gone another way. And it's conceivable that you may not actually even close up. Okay. So the question being, can you spot a closed geodesic here in this S2, meaning this is topologically an S2, that's pretty clear, but the metric is the metric induced from R3. So it's not the standard S2, obviously. So these kind of examples are right in front of you. So let's keep it at that. Let me ask a different question. Does there exist infinitely many periodic geodesics for any metric? Okay. So I should be clear here. When I say periodic geodesics, I obviously mean distinct periodic geodesics. Okay, so if I take a geodesic gamma and gamma square, they of course give me the same. They of course give me the same. I would call them the same geodesic because the image of gamma and the image of gamma square are the same. So I mean distinct periodic geodesics, and I'm asking whether there are infinitely many of them. Forget one of them. Okay, so it's an even stronger question. Fortunately, the answer in some of the cases is in the affirmative. Okay, so allow me to move on to the next slide. So this is the first affirmative answer in this direction by Gromol and Mayer, where they use equivariant Morse theory to say that yes, this is true for any metric if the manifold is simply connected and the manifold is closed. So closed, let me remind you, means it's compact and without boundary. Simply connected already means it's oriented. And there's this condition that the Betti numbers of Lm, namely you look at the singular homology of Lm or the singular cohomology of Lm, take its dimension. So these are the Betti numbers of the free loop space. This is Lm. This sequence has to be unbounded. So it basically boils down to knowing how to calculate these things and checking whether these are unbounded at all. If that happens, then yes. Okay. So in general, how do you even check something like this is true? Well, the follow-up result of Vic Poirier and Dennis Sullivan from '76, this used rational homotopy theory, tells us that if your cohomology ring of the manifold, so this is H dot, so H upper dot means this is the direct sum of H0, H1, H2, this is the whole graded cohomology ring. So the cohomology groups of a manifold or a space form a ring using the cup product or the wedge product of forms. And if this ring requires at least 2 generators as a ring, then the answer is yes. Okay. So this is something that is easy to check, right? So for example, if you take spheres, the cohomology ring of a sphere is generated by one element. The cohomology ring of CPN is generated by one element. So these do not fit into this category. Okay. And in fact, for a sphere, one can show that the Betti numbers of LM are actually not unbounded. So for spheres, neither one of these two theorems apply. Okay. So, and then Lambrecht later on actually modified this for specific connect sum operations. So you can do a little bit more, but you know, the question remains, what about S2, right? I gave you an example of this bumpy S2. So is it true that there are non-trivial closed geodesics there? So it has a long history. I think in 1927, a group of people claimed, I think Fate and Lustenik and maybe others claimed that there is at least 3 non-trivial closed geodesics on S2, but it was incomplete and things took a long time to settle. And then in 93, using works of Franks, Bangert, and then independently Hingston showed that yes, there are infinitely many distinct periodic geodesics for any metric on S2. But their proofs was not just using differential geometry, it was using dynamical systems and ideas from those fields as well. So it's true. Okay. Okay. So this brings me to one point of confusion which is often there in the interface of differential geometry and algebraic topology, especially in this context, that whenever people talk about this dimension of HK of LM, sometimes there's a chance of confusing this LM with this particular space, omega M. Okay. And what is omega M? Well, omega M is called the based loop space. That's another object in our study. It's based because these are not all maps of circles to M. These are all maps of circles to M which start and end at x0. So it's just a smaller subset, okay, much smaller subset. So the space of loops is much bigger. Here we are asking the loops to start and end at x0. So there's a confusion because this space and the free loop space are completely different. And usually you can have a hold on what the Betti numbers of these are if you know it for M, but you cannot really control anything about LM in general. So these two are quite different objects, okay? But for some reason there was some confusion in the literature and otherwise. And so if you replace this answer or theorem of Bromolmeyer with Betti numbers of omega M, then this theorem is of course not true. So this is an entirely different thing altogether. But how does this based loop space enter the picture? Well, let's do a simple map. Let's take this map evaluation from the free loop space to M. What does it do? It takes a loop and it sends it to its image at 1. So it just looks at the base point of the loop, right, where it starts and ends. So this is it's a smooth map, and it turns out this is locally a fiber bundle, or it's locally a bundle. If you have seen bundles, then this simply means that locally LM looks like M cross this thing. Okay. And what is evaluation inverse of x0? Evaluation inverse of x0 is going to be precisely omega M, all loops which start and end at x0. Okay. So by saying it's a fibration, I mean that LM locally looks like M cross omega M. So of course, omega M is secretly x0 here, but for any x0, I get different omega M's. They're all homotopy equivalent. They're all loops based at different points, but you can go from one to another. Okay. All right. So let me continue talking about based loop spaces. So based loop spaces basically is due to seminal results from the late 1950s. Bott had done some work, and among those it includes Bott periodicity, and he proved pi 2 of a Lie group is 0. And he also introduced more spot theory. On the other hand, in homotopy theory, the based loop space is a central object of study. Okay, it's just an important object there, and there are various properties that one uses. Okay, that there's an adjunction, which if you haven't seen, it's fine. This is something very useful. Switches the homotopy groups of X to homotopy groups of the based loop space, and it's an H space. Okay, so So H space means it has some extra structure, meaning it has a multiplication map. What is the multiplication map? Given two loops, you concatenate, right? Okay. What is the dual map or the co-algebra map? Well, the co-algebra map is simply the diagonal map. Given a loop, you just take alpha comma alpha. This diagonal map exists for any space. A goes to A comma A. So these two maps combine in a nice way and form what is called an H space. And in fact, if you have seen this example, if you take homology of this space, which you can always, it turns out to be much more than just a co-algebra. It's actually a half algebra, because all these maps combine in a nice way to give you a lot of structure. It's an algebra, it's a co-algebra. The co-algebra map is compatible with the algebra map in a certain nice way. Okay, so there's this slide that I would want to just maybe briefly go through. So since we talked about homology, I want to talk about the chain complex which gives rise to homology, right? So homology comes from chain complexes, for those who have seen algebraic topology. So this is just a singular chain complex. Delta is the usual boundary map. If you take its homology, what you get is the homology of omega x, right? So one can check that this boundary is actually compatible with the multiplication map. And I mean, I hope you'll trust me when I say this. So that's what this means, that you can multiply two chains and then take boundary, or you can take boundary in this fashion and then multiply, it will be the same. All that means is that the homology of omega x becomes what is the half algebra. So it has incorporates all these extra structure of M and delta. Okay, we'll use this later on in a moment. So this is what I was talking about. So this is the Pontryagin product, right? Which is the usual product of loops. Alpha times beta is alpha travel twice as fast, beta travel twice as fast. So you have all seen in a course in algebraic topology that if I take three loops, I can combine them in either of the two fashion, and these are homotopic. But these are not homotopic. So yeah, just forget the last line, it's a glitch. Just focus here. So this is alpha dot beta gamma, and this is alpha dot beta dot gamma. And a homotopy would be a way of going from this loop to this loop, parameterized over interval 0, 1. So there are several choices. This is one choice. Why is this a choice? Because at every S, I basically give you a subdivision of the interval 0, 1 into 3 intervals, and I use this much length for alpha, this much for beta, and this much for gamma. And this is a homotopy between these two loops, right? But there are lots of choices. This is another natural homotopy. So you have to make a choice. When you say these two are homotopic, to make a choice, assuming you have made a choice, what you get is a map from the interval cross 3 copies of omega x to omega x. Why is that? Because every point in the interval, which is S, gives me a way of subdividing 0, 1 into 3 intervals, and that gives me a way to combine 3 loops into 1 loop, as the picture suggests. So what about 4 loops? How do I combine these 4 and these 4, and how many ways are there? It turns out there are 2 different ways to do this using this fixed choice, and they're both homotopic. So let me show you this picture. Okay, so there's the picture, and you can have a look at it while I speak. So you can go from the left bracketed system to the right bracketed system, either by using the M3 that we have defined in 3 moves, or by using M3 using 2 moves. And these are 2 different ways of going from the left bracket to the right bracket. But these 2 ways are all, again, homotopic amongst each other. So which means is that this entire pentagon can be filled in. What does that mean? Well, that simply means that there's a map defined over this pentagon cross 4 copies of omega x to omega x. So K4 is just a notation for this pentagon. Okay. So K4 is just the convex polyhedron which governs how many ways you can combine 4 base loops. It turns out in general there are these objects called Kn which govern how many ways you can combine n base loops, and I'll call them Kns. Okay. So this brings us to the next topic, which is what are these Kns and what kind of a space is omega x? It has way more structure, as it seems, than just being able to combine things one way, because the next time you'll try to do this, you'll see there are 5, you'll take 5 base loops and you'll see how many ways to combine them and what are the objects that we get. So this is what leads us to associative up to homotopy. So this is a definition defined by Jim Stasheff in the early 60s, motivated by this study on H spaces and base loop spaces. So he calls this an AN space. What we are interested in are going to be A infinity space, which is an infinity here, as you saw in the first slide. So an AN space is nothing but a space X and a family of maps Mi from Ki cross I copies of X to X. What are Ki's? Well, Ki's, you have already seen the first two. K2 is a point, K3 is an interval, K4 was a pentagon, and then K5, we don't know what it is, and then there are K6, K7, and so on. Okay? So the important thing is M2, the first map is really a map from X cross X to X because K2 is a point. So M2 is has to be a multiplication with a unit, but everything is up to homotopy. Okay, so the unit is up to homotopy. The multiplication is just a multiplication. And then there's a third condition which looks a bit obscure, but this is how it's presented in STASHF. And because algebra is always typically bereft of pictures, but what this says is something very simple. It says these KIs are actually somewhat, like prescribed. So if you take any KI, then each KI in its face will have things of the form KR cross KS. And this is just saying that if you restrict the Mi onto the boundary of Ki and combine them, it's amounting to asking, like computing the Mi's on using the previous data. So let me give you a picture instead. So K2 is just a point and you get a map from X cross X to X. What is K3? Well, K3 is just the associator between A dot BC and AB dot C. What is K4? We already saw that picture. This is what K5 looks like, okay? So if you take K5, then you look at 5 plus 1, that is 6. And then the faces of K5 are going to be either K2 cross K4 or K3 cross K3. So what is a K2 cross K4? A K2 cross K4 is nothing but a pentagon. A K4 cross K2 is also nothing but a pentagon. And a K3 cross K3 is exactly a diamond because K3 is an interval. So you see 3 diamonds as the faces and 6 pentagons as the faces. So this is exactly, if you go back and think about it, this is exactly a compatibility condition, saying that the MIs are not independent. The MIs restricted to the boundary should be defined in terms of the previous MIs in the appropriate sense, okay? Okay, so it has some nice pictures, and these polytopes, by the way, are called STASHF, like polytopes, or STASHF associahedra. It was rediscovered by him in the 60s while he was working on these things. It was earlier discovered by Tamari when he was working on Tamari lattices. Okay, but to come back to our A infinity setup, what is an A infinity space? Well, it's a space where these MJs exist for all J. So M2, M3, M4, all the way. And examples, of course, groups are examples because it's associative strictly, so you don't need any higher correction homotopies. Monoids and base loop spaces, obviously. Okay, and I'll sort of leave you with this quickly because I want to get to the other main point. So an important result of STASHF is that if you want a characterization of A infinity spaces, namely if I give you a space and ask you to check if it's an A infinity space, how do you check it? So he proves that a space is an A infinity space if and only if it is homotopy equivalent to a base loop space. In fact, this X can be defined in terms of Y itself. So effectively, up to homotopy equivalence, an A infinity space is as good as a base loop space. That's what he's saying. So omega X is the prototypical example. It's also in some sense the only example. Okay. But the key thing that was observed by his work is that associativity is not a homotopy invariant. So if you like homotopy invariant things to work with, associativity is not a homotopy invariant. For simple reason, if you take a homotopy equivalence between two sets, one is a group, the other one is just a set, use the homotopy equivalence to transfer the structure. The structure that you get on the set is not going to be a group anymore, in the sense the multiplication is going to be associative up to homotopy and higher homotopies and so on. So that's what we mean by this, okay? But you do want to transfer structures. So what you want to work with is the notion of A infinity or associative up to homotopy, but not strict associativity. That's the key upshot of all of this. And then this went into several directions. There was work by Boardman and Vogt and May, initiating works by others in the topological setting, how to recognize iterated loop spaces. And then there was the direction of proper adds and other homotopy algebras. So A is not the only alphabet that you can use. You can use C infinity, C for commutative, L infinity, L for Lie, and so on. Okay, so it has a huge history and it has a strong imprint on mathematical physics as well. So that's a direction which this has taken a strong stride towards. So, but just to give you one point of view for those who are algebraists in the audience, we often take homology and cohomology of spaces. So what about homology and cohomology of algebras? Well, it turns out there are certain theories of cohomology and homology for algebras. And so, associative algebras are usual algebras without a differential, but sometimes we talk about DG algebras. So G stands for graded. You can take the example of differential forms. There's a grading, there's a de Rham differential, and there's a wedge product. So it's a differential graded algebra, right? So DG algebras means that. And then you can take chains on the base loop space. That's also a differential graded algebra, not an associative algebra. Okay? The point is that for associative algebras or even A-infinity algebras, there's a notion of homology called Hochschul homology and a notion of cohomology called Hochschul cohomology. And this has its own origins. Let me not get into that, but there's a result due to Burgelia and Fedorovich and Goodwillie. So just take it as a black box, whatever these things are, okay? Like cohomology theories, the Hochschul cohomology has nice algebraic properties like cup products. The Hochschul homology does not have these cup products, okay? Just comparing with the standard homology. But in 86 and 85, in a way simultaneously, Burgelia, Fedorovich and Goodwillie, Tom Goodwillie, they proved that there are isomorphisms of graded modules. Namely, whatever this black box is, the Hochschul homology, the kth degree of this algebra, the chains of the base loop space, is nothing but the kth homology of the free loop space. Remember, this Betti number was something we did care about at some point in the beginning. So although this might be hard to compute, this is saying that the kth Betti number of LM can be recovered if you knew how to compute the Hochschul homology of the chains of the base loop space. So this gives you some connection why we might care about the Hochschul homology or cohomology of C star of omega x, okay? But again, this is just for every k and there's no extra algebraic structure on either side as of now. But keep this in mind, we'll come back to this, okay? So this brings me, so this connection brings me back to the fourth object of my talk, namely the free loop space, which we already talked about. So the free loop spaces, remember, is all maps from circle to M with a compact open topology. Well, you should also recall the fibration that we talked about. We talked about the evaluation map, takes a loop, sends it to its base point, gamma goes to gamma 1. And this is written in this way. This simply means that the inverse image of a point is simply the loops based at that point. And LM should be thought of as a union of these omega m's, all loops based at different points as the point varies over M. That's a picture. Okay, excuse me. So we would like to define some sort of algebraic structures on the free loop space. So you can be naive and say, what can we do? Well, we could do what we did for omega m, take two loops and just concatenate them. But if you think for a minute, you cannot do that in the free loop space, because if I take two arbitrary loops, they may not start at the same point. So concatenation doesn't even make sense if two loops start at different points, right? So what can I do? Well, I can try to do this in families, because on M, I can intersect families transversely. This is what transversal intersection does. On omega M, I can combine families if they start and end at the same point. So I want to combine these two operations. So I start with families. So alpha and beta are families of loops. Alpha is an I-dimensional family. Beta is a J-dimensional family. I look at evaluation alpha, evaluation beta. So what are they? They're simply the images or the shadows of alpha in M and shadow of beta in M. So these will give me I and J dimensional families M itself. Inside M, I can put them in general position, intersect them transversely, and get a I plus J minus D dimensional family, because D is my dimension of M, right? So if I take a generic I family and J family of, the I dimensional and J dimensional like subset inside M, intersected transversely, its dimension is I plus J minus D. And for each of those intersection points, I could combine the alpha loop with the beta loop, because now I can use the fact that they both start and end at the same point. What I get is a I plus J minus D dimensional family in LM, right? So I hope this, so I mean, here's a picture if what I said is not convincing. Just imagine a blue family of loops, which is a two-dimensional family, and the green planar region is the base point evaluation alpha. And here's this orange family, a one-dimensional family of loops. And this brown line is evaluation beta. And clearly the brown line intersects the sheet exactly at one point, namely this point. And I can combine the blue loop followed by the orange loop. What I get is one single loop. It's a zero-dimensional family. So it's just a point in LM, but a point in LM is a loop. So that's a picture. Okay? So of course, one has to be a little careful, make all of these things precise, because you have to make things transverse, combine them. This can be done. So this is the theorem of Moira, Chas, and Dennis Sullivan in 1999, where they prove that the loop product defines a graded commutative associative algebra structure on H dot of LM. Okay. So this is the paper which was seminal in the sense that it kickstarted this field of string topology, which is basically the study of algebraic and differential topology of free loop spaces. So it has a product structure called the loop product, but you have to do it with families. You cannot do it, point by point. Okay. So we'll see what this is in a moment. So this is nice. Okay. So it combines, as I said, the Pontryagin product of the base loop space along with the intersection product in the base manifold, because you're really combining both these things. And you can check that this algebra has an identity, the class of constant loops. But there are further structures. Okay. So what are these further structures? Well, remember there's a circle action on the loops. You can take a loop, you can rotate a loop and then map it in. So gamma is a map from S1 to M. You could pre-compose with a rotation and then map by gamma. So that gives you an action of the circle. I mean, physically, it just means you rotate the loop before you map it in. As simple as that. So that actually induces an operator delta from HK to HK plus 1. This is called the BV operator, as you'll see. But this has two properties. One is del square is 0. This is a nice bit of exercise in algebraic topology if you want to think about it. And there's this mysterious 7-term relation. This one term equals these 6 terms on the right. So for those of you who like algebra, you might have encountered this. For those who haven't, this might be very, very mysterious. This doesn't even look anything remotely like things you might have seen. This has a geometric sort of meaning and a geometric origin. Maybe I can talk about it later if there's time. But such an algebraic structure has a name. It's called a BV algebra. Butlin-Vilkovsky, named after two theoretical physicists who were studying these structures even before they were defined here, based on their interpretation of some physical phenomena. So anyway, so what we get is this structure. So we have all these structures. So the question is, can we compute some of these things? What can you say about these structures? Are they homotopy invariants? What other invariants can we get? Okay. But before that, let me just throw in a question. The question is the following, that remember I said that the Hochschild cohomology of A, where A is an associative algebra or a DG algebra, has a lot of algebraic structures. One of the algebraic structures that appears in the Hochschild cohomology of an algebra is that it has a canonical BV structure. I didn't say what it was then, but I can say it now. So whatever this structure is, and remember there was some identification between the Hochschild homology of the chains of the base loop space along with the homology of the loop space. But now we are saying that the homology of the loop space also has a BV structure. It's quite natural to ask, can one somehow reconcile these two structures where A is the chains on the base loop space? Because this is somewhat algebraic, and this is something coming from the construction of how you rotate the loops. So this is a question which maybe we'll address later, okay? But it's there since we discussed BV. Okay, so of course, in terms of computations, not much is known about computing this, even if you ignore the BV operator. There are a few computations on spheres and CPNs, and perhaps a little bit more, mainly due to Cohen-Jones and Ian, but nothing more, okay? So one would still like to compute more examples. On the other hand, if you are looking for interesting sophisticated invariants, then the theorem of Cohen, Klein, and Sullivan says that this loop product dot is a homotopy invariant. So you cannot expect non-homotopy invariants through loop products. Okay. So in fact, one of the original motivations of defining this loop product and string topology was to come up with non-homotopy invariants. But this theorem says that the loop product is not the place to look for that. Okay. So how do we search for non-homotopy invariants? That's a question. And I'm going to give you a template, but this is still a bit imprecise, like most templates are. You have to work through the details and see what you get. One way to do this would be to incorporate geometric constraints into the space you're studying. So you don't want to study the full loop space. You want to study certain subsets. defined by geometric constraints with the hope that you extract non-homotopy invariants or geometric invariants, not topological invariants. Okay? So here's something that I could do. You could take a loop. A loop is nothing but the upper hemisphere of the circle and the lower hemisphere of the circle, both in tandem mapping to M. But I could imagine this map as a map into M cross M, where I map both these two strands simultaneously, right? So I just take gamma of t and gamma of 1 minus t and map it simultaneously. What I get is a curve in M cross M, starting and ending on the diagonal. So this is the picture. So once I have this picture, I could basically now say, okay, I don't care about the loops here. I only care about arcs in M cross M, starting and ending on the diagonal. And I can impose certain constraints, like I want the arcs to be perpendicular to the diagonal when it hits it, or I want the arcs to be in a specific direction to the normal when it hits it, and so on. So I could impose all sorts of extra constraints on the arcs when it hits the submanifold, and the submanifold could be something else. It need not be the diagonal submanifold. I could enlarge this game quite a bit, but then the problem is you have to define a theory which involves how to split the strings, how to glue the strings, what is the analog of the loop product, how does the circle act, and so on. So one has to work through all of those details. And there are some instances where this has turned out to be interesting and important. So this has some chance of being true, but one has to work in the specific context. So you have to essentially modify LM to be something inspired from geometry. Okay, so yeah, I mean, if there are questions later on, I'd be happy to talk more about this. But there's one other thing. So the circle action, remember, acts on the loop space. So for those who have seen equivalent homology, whenever a group acts on a space, you can talk about the G equivalent homology of that space. So whatever that is, we are going to focus on a very simple aspect of this. So you take again two families of equivariant loops. So equivariant loops means these are directed loops, but equivariant means that there is no base point. So the base point is gone. So any point is as good as a base point. Okay. So what can I do? I can put markings everywhere. So any I-dimensional family creates a I plus one-dimensional family, because I've put a marking everywhere. So each equivariant loops gives me a one-dimensional family, a circle worth of equivariant loops. I can intersect these using the loop product. I get a I plus j plus 2 minus d dimensional family of actual loops, and then I ignore the marking. Okay, I ignore the marking. What I get is an equivariant family of loops. I denote this by bracket alpha beta. So again, as before, this has to be done carefully and precisely to show that this is well defined, but it can be done. And the theorem of Chas and Sullivan says that the equivariant loop homology, whatever this gadget is. So in case some of you may be confused, this is not the homology of LM quotient out by the S1 action, okay? Because that is true if the action is free, but the S1 action on the free loop space is not free. So this is something else altogether, but this turns out to be a Lie by algebra. So it's a Lie algebra, and there's a co-product which satisfies a co-Jacobi and so on. I'll give an example of that in a minute. But it's something more than a Lie algebra, but in particular, it's a Lie algebra of degree 2 minus d. Okay, so it's a nice bit of structure that you see coming up if you go to the equivalent settings. Okay. So the question is, okay, what is this structure? We have defined some abstract things without much pictures or without much insight into how these are well defined. So let's take the simplest possible route. Let's do it for surfaces. Okay. So what should this be for surfaces? Well, M is a surface. D is equal to 2, D is the dimension of M. So this is 2 minus 2, so this is degree 0. So what you get is a Lie by algebra of degree 0, meaning you have a bracket, a co-bracket, they're compatible, and it determines something on whatever these objects are. Okay, so let's see what that is. So that brings me to my last object in the study, which is sigma, the case for surfaces. So sigma, as usual, is going to be closed, connected, an oriented surface of genus 2 or more. I'm not going to stick to spheres or the torus. Torus can be handled easily, and the spheres, because of being simply connected, can be handled by other means, and it doesn't fall into this sort of family of results. Okay, so so one thing most of you would know, at least those attending the topology session, is that any such surface is an example of a k pi 1, meaning that there are no higher homotopy groups, right? All these Riemann surfaces. And one can show that the components of the loop space, so the loop space will have lots of components. The components are indexed by free homotopy classes. or conjugacy classes if you like conjugacy classes more, they're equivalent. In fact, one can show that the components of this are homotopic to circles. So they are fat, but they are basically look like circles up to homotopy. Okay. And one can in fact calculate the equivalent homology of this, whatever this is, just from definitions with a little bit of work, show that with rational coefficients, the equivalent homology is concentrated in degree 0 only. So all the extra degrees are no longer relevant for us. Okay? So what are we asking? We're asking what is this Lie bialgebra structure on whatever this quantity is. But just take a minute and think about what this quantity is. What is this? Well, this is the 0th equivalent homology of L sigma. But forget equivalent. What is the 0th homology of L sigma? These are just points in L sigma, path components. And equivalent means you just take an element of L sigma, remove the marking. That's all. So these are simply directed, unmarked loops. But we are allowed to work in L sigma. In L sigma, any two loops are path connected if and only if they're freely homotopic to each other. So we're really looking at free homotopy classes of loops. So this space is nothing but the vector space generated by the free homotopy classes in pi 1 sigma or the conjugacy classes in pi 1 sigma. Okay? So it's just that thing. You take the pi 1 sigma, take its free homotopy classes or conjugacy classes, take the free vector space generated by those elements. So what we get, we should be getting a Lie bracket and a co-bracket. So instead of defining it formally again for you, let me show you in terms of a picture what we get. Okay. Hopefully that will convey more than, because I already said what it is in the abstract setting. So this is due to Goldman. So by the way, so the string topology gives you these things, but the study of string topology or loop spaces by Chas and Sullivan is motivated by the works of Goldman and Turaev. And this is what motivated them to generalize it further. So this is the beginning point, that Goldman in '86 showed, among other things, that if you take two curves which are placed in general position, the red curve and the blue curve, it has double intersection points and the surface is oriented in a clockwise manner, meaning that the normal points inward if you take the right hand rule. At every point you go and see what is the orientation given by A followed by B. Well, it's clockwise here, so there's a plus sign. It's clockwise here, there's a plus sign. And now what you do is you start following the A curve until you come back to the A curve, and then you follow the B curve. So you can only resolve it one way exactly to get an oriented curve. And these are the two pictures that you get. So the Lie bracket of these two curves will be this curve plus this curve. Okay, and these are oriented curves, but these are unbased. That's why there's an arrow and no starting point. Okay, and it turns out this will be a Lie algebra. Okay, so what about the co-algebra? Well, the co-algebra by Turaev is something similar. You take a loop and you split it into each of its double intersection points. So if I split it here, I'm going to get these two. If I split it here, I'm going to get these two curves. Okay, and of course you have to skew symmetrize these things appropriately, but you can do that. So that's what Turaev does. And if you combine these two things, modulo some details that I'm going to skip, you're going to get the Lie bialgebra that was described in the abstract string topology setting, but specialized to the case of surfaces. Okay. So, I mean, these are nice pictures that you can think about and recover the other things. Okay. Okay. So just one more slide and I'm done. So the Lie bialgebra is associated to surfaces. There has been work on this by a lot of other people in different directions in combinatorial topology and connecting probability with self-intersections. Very nice works. But connecting it all to the Hochschild cohomology, there was a result by Weintraub which says that if M is a KG1, our surfaces are examples of that. The Hochschild cohomology of the group ring, so KG simply stands for the group ring where K is a field. The Hochschild cohomology of this algebra is isomorphic as BV algebras to the homology of LM as BV algebras. So this was the thing that I was hinting towards. So if you replace this with cohomology and not homology here, then this is an algebra, this is an algebra, it's an isomorphism as BV algebras, which is very nice, right? Provided K is, let's say, Q. But this is very specific to manifolds of the form KG1, not for other kinds of manifolds. Okay. But finally, let me take one full circle and finish up where we began. We started off with closed geodesics, and let me finish on a simpler note by asking, okay, what are the closed geodesics on the surfaces that we have been talking about? Well, Our surfaces are genus 2 or higher, closed oriented. So you can put a negatively curved metric on sigma. In fact, you can put a metric of constant curvature -1. For each free homotopy class, you can find a closed curve in that class, which minimizes the length. And this, it turns out, is unique because of the negatively curved property. And this is also a geodesic. That's what Borkov is telling us. So in fact, for every free homotopy class, there's a unique geodesic in that class. Okay. So we know what closed geodesics look like on surfaces, provided you choose nice enough metrics. Okay. So this brings me back to where we started. So thank you for your attention. So we can't hear you, I guess.
Yeah. So thank you, Somnath, for this wonderful talk. And so now any questions? So please ask Somnath.
I have a question. Yeah, can you hear me?
Yeah.
Yeah. So the range of result, when you said M is KG1 and the half-chair homology is isomorphic to the loop space homology,
Yeah.
is there one equivariant version of this? Because if I remember, half-chair homology sort of admits also
I see. So there might be. So I guess, yeah, they have. So the Hofschuld's thing has this cyclic action, and so usually you want to replace the cyclic action. I mean, corresponds to the circle action on the loop space side. So I am not aware of any result on that note for the KG1 spaces. I mean, but it's I mean, now that you point out, it's definitely probably something that one should think about, and I am not aware of any such results. But yeah, if there is such, I mean, that would be very interesting to note actually. But on the other hand, if you see, I mean, I guess the main point would be to look for what it does for KG1 spaces, because for surfaces, the Goldman bracket over Q, for example, is.
Sheila, so I think this is Sheila. So can you mute yourself?
Yeah, I'm sorry.
So
Okay.
I mean, on the Goldman bracket side, I guess the Lie algebra, there's still a lot of things that one would like to sort of say anyway regarding characterizing what are the structures and so on. But yeah, so I mean, your question is very interesting and very important. But I mean, I'll think about it. But I don't know of any reference that comes to mind. Yeah.
okay. Okay. And another one, you said that earlier you stated a result that if you can compute the Betty numbers, then probably you know that there is a closed loop, right? Closed geodesic, if I remember correctly.
Yeah.
So does this extra structure helps you to compute the Betty numbers in some way?
No, does this like, can you say that again? Does this?
So earlier you said some result, if I remember correctly, that if the Betty numbers are unbounded.
Yeah, right.
Yeah.
So that is Gromol-Mayer's result. So the point is that usually to say that the Betty numbers are unbounded, you need to have some techniques. So one technique one could try is like take a rational, model of the free loop space from rational homotopy theory, try to write down the generators relations and then compute it. But that typically gets out of hand very soon. On the other hand, if you go by this dictionary of Hofschuld homology or cohomology, then one could try to compute the Hofschuld cohomology of an algebra. But even those computations are usually very hard. But there are some computations regarding bounding or unbounding the Betty numbers of LM, but it usually requires a combination of techniques either from homotopy theory or from rational homotopy theory or homological algebra. But some amount of these things are known. Plane 4 manifolds or highly connected manifolds, one knows that these Betty numbers are unbounded, and hence they have infinitely many distinct periodic geodesics. So, but not in the general case. There are some conjectures of Gromov regarding that, but I think for the most part that is open.
Oh, okay. Okay. Thank you. Thank you.
So are there any other questions?
Hello.
Yeah. So I think this is Ankur. Yeah. So.
So
which you have defined, is it will be a fiber bundle if M is non-compact?
Yeah, it is. I mean, it has nothing
Yeah,
to do
sure.
with, so yeah, that's a good question. It's nothing to do with compactness. So what you have to show is that locally, you see, all the fibers are homotopy equivalent because omega M at x0 and omega M at x1 are homotopy equivalent. But one has to show that locally this looks like U cross omega M, where U is an open subset of M. So I mean, it doesn't really depend on M being compact. But you need M being compact in the whole analysis later on because you want to talk about the fundamental class of M. And the fundamental class of M is very important because it generates the identity of the loop product. If M is non-compact, then there would not be any identity in the algebra. So that's partly why you need M to be oriented and compact as well. Okay.
One more question is that so the base loop space has H-space structure, right?
Yes.
And LM, that free loop space you have given a structure. So if the structure, if I restrict the structure of LM on the base loop space, can we get the H-space structure?
Yeah, so see the structure on LM is really not on LM, but it's on the homology of LM. That's what I said, right? You cannot combine two loops in LM directly because they may not start and end at the same point. But see, there's this phenomena that there's the inclusion of the base loop space inside the free loop space, right? And the base loop space has an H, so it induces a map in homology, and one can show that this map in homology is actually a map of algebras, that the H space structure is compatible with the loop space structure there, up to a shift of degrees and so on. So yeah.
Thank you.
Okay, so are there any other questions?
There are some questions which were asked. I have written them in chat box. Can you see them?
Oh, achha. Can you run a spectral sequence?
3 questions are there.
Oh, three, huh? So is there an intuitive way to expect only hits to Oh, so the first question, I guess, is how hard is it to check the Betty number on H star LM? Yeah, so I partly answered that. So I guess the point is that H star omega M, as rightly pointed out, is the universal enveloping algebra, but then H star LM is quite different from that. And as one knows from examples in 4 manifolds and so on, if you take any 4 manifolds of second Betty number at least 3 or higher, then the Betty numbers on LM actually grows quite fast. So, but omega M is quite controlled because it's somehow controlled by M and the homotopy groups of M, because the homotopy groups of M and omega M are the same. So in general, the Betty numbers of LM is a slightly different sort of object, algebraically or otherwise, compared to omega M. So in general, in Gromov mesh, there's no condition, but there's a conjecture of Gromov which says that you expect the Betty numbers of LM to grow in a certain rate, provided your manifold is generic. So generic means that it's rationally hyperbolic. You can look it up. And the metric is bumpy. So you do not expect these kind of arbitrary growth, unbounded growths on the Betty numbers for any manifold and any metric. There are, there are genericity constraints there. So that's what is known on that context. And yeah, so how hard is it to check? Yeah, so H star LM, I don't think there's any general techniques to compute H star LM. I mean, there are obvious theoretical methods, but you cannot really compute with any one of them, practically speaking. You need different techniques. So you have to model M and then use a bit of homological algebra and so on. The last question is, can you run a spectral sequence on M to compute the algebra completely? No. So the point is that, see, I mean, there is a spectral sequence which Cohen-Jones and Yan uses to get the loop product on LM, but there are some extension issues like it is in any spectral sequence, and they only managed to do it for CPN and SN, and that's where they managed to compute the full loop product algebra on H star of LSN or H star of LCPN. But in general, I mean, even there you have to know H star of omega M really well, H star of M, and if H star of M has a lot of generators, then you'd be at a loss to even control the maps. These works very well for SN and CPN because these are monogenic manifolds. The cohomology ring is generated by one element. That's why things simplify. So there is a spectral sequence, but I don't know how useful it is for practical computations. Okay, so I think these are the 3 questions they have. Yeah.
Okay. Thanks, Somnath.
Thank you.
So, yeah. So thanks, Somnath, for this nice talk. So.